Have you ever paused to consider the incredible journey electricity takes, before it powers your home?
It's quite something, isn't it?
Yeah, it's generated at some massive power plant, maybe hundreds of miles away. But then flick a switch and bam, your lights are on, your phone charges.
Everything just works seamlessly.
Exactly. So what's the unsung hero behind all that? That piece of tech working tirelessly, moving power across huge distances without us really noticing.
Ah, you're talking about the transformer.
That's it. Today, we're doing a deep dive into the world of transformers.
Those boxes you see everywhere.
Right, perched on poles, tucked into substations, even shrunk down in your charger. Our mission here is to really, demystify these things.
Understand what they are, how they tick.
Exactly. How they function, why they're so absolutely vital to modern life, and maybe the most surprising bit,
Sure.
why they look, well, simpler than you might expect.
It's true, the design is quite elegant in its simplicity.
We're going to peel back the layers, reveal the genius hiding in plain sight.
And what's fascinating here is how something so ubiquitous can just fade into the background.
Totally taken for granted.
Right. We use the results constantly, but the device itself, invisible. It's definitely one of the unsung heroes of our electrical grid.
Couldn't agree more.
And for anyone curious about the hidden engineering that makes our world work, well, digging into transformers is really rewarding.
And maybe not as complicated as people think.
Exactly. The core ideas are surprisingly straightforward. It's basic physics applied cleverly.
Okay, so let's start right at the beginning. What is a transformer, fundamentally?
Well, at its heart, it's an electrical device, right? And its job is to change electrical energy
Change it how?
by using a changing magnetic field.
Ah, that phrase again. Changing magnetic field. That sounds like the key, doesn't it?
It absolutely is. It's the dynamic element, the engine driving the whole process.
Okay, but before we dive into the how it uses that changing field, let's tackle the why. Why do we even need to change electrical energy like this?
That's a great question. Why not just send the power out as is?
Yeah, why can't the power plant just generate it, say, 120 volts and send it straight to my house?
Well, it boils down to physics, really. The problem is energy loss over distance.
Like friction.
Sort of, yeah. Think about electricity traveling through wires. Those wires have resistance, right? And when electricity flows through resistance, it generates heat.
Okay.
So if you try to send electricity, especially at the low voltage you use at home, over really long distances, hundreds of miles, a huge amount of that energy gets wasted as heat.
How huge?
Astronomically huge. It's called joule heating, or sometimes I squared R losses. Basically, for the same amount of power, if your voltage is low, your current has to be high. And high current means massive heat loss in the wires.
So it would just be inefficient.
Terribly inefficient, economically disastrous, environmentally problematic, just not practical for powering cities from distant plants.
Right.
And this exact problem was actually the core issue in that famous current war back in the late 19th century.
Edison versus Tesla, right? DC versus AC.
Exactly.
Okay.
Edison backed direct current, DC. It worked fine locally, powered the first light bulbs in New York, great stuff, but
you couldn't easily change its voltage.
bingo. That was DC's Achilles heel for long distances. It meant power plants had to be really close to the users. Imagine tiny power stations dotted all over a city.
Messy. And probably smoky.
Very. Then you had Tesla and Westinghouse championing alternating current, AC. And AC had a secret weapon,
The transformer.
the transformer. It was the game changer. Without it, AC wouldn't have had that crucial advantage. A big power plant miles away. Useless without a way to efficiently move the power.
So without transformers, the power plant really would need to be next door.
Pretty much. Or we'd be living in a vastly different world. Less electricity, less development. Transformers are the key to moving power efficiently across those huge distances.
It really is staggering, the impact of one device. Okay, so we know why we need them. Now let's get into the how. That changing magnetic field. How does that work?
Right. So picture the transformer as this clever mediator. It passes energy along without the input and output ever touching electrically.
Okay.
On one side, you've got the input, the primary coil. That's where the AC power comes in.
From the grid or whatever source.
Exactly. Now, when that alternating current flows into the coil, it swirls around, right? And moving electricity creates a magnetic field.
Like an electromagnet.
Precisely. We call this field magnetic flux. Think of it as invisible lines of magnetic force filling the space around the coil.
Okay, I could picture that. Invisible force lines.
And because it's alternating current, which is constantly changing direction and strength,
The magnetic field must be constantly changing too.
you got it. It's expanding, contracting, reversing polarity, pulsing with the rhythm of the AC. It's a dynamic field.
Okay, so step 1. AC in the first coil creates a changing magnetic field. What's next?
Next comes the iron core. This is crucial. This changing magnetic field isn't just left to spread out randomly.
It's guided.
Exactly. The iron core acts like a super highway for magnetism. It concentrates that magnetic flux and channels it very efficiently over to the other coil.
The secondary coil. The output side.
That's the one. The iron core is like the delivery person, making sure that magnetic energy gets where it needs to go.
And what happens when it gets there? To the secondary coil.
This is where the real magic, the electromagnetic induction happens. That secondary coil sits there, and it feels the change in the magnetic field passing through it via the iron core.
It feels the pulsing, the reversing.
Yes. And in response to that constant change, the coil generates its own electricity.
Wow. So the changing field makes the second coil produce power.
Precisely.
Yeah.
And because the magnetic field is changing in sync with the primary AC input, the electricity generated in the secondary coil is also AC.
Okay, that makes sense.
When the input voltage reverses polarity, the induced voltage in the secondary reverses too, so you get AC out, and critically, it's at the exact same frequency as the input AC, like 60 hertz in, 60 hertz out.
So it's not the magnetic field itself, but the change that does the work.
That's the absolute key takeaway. Constant field, nothing happens in the secondary. Changing field, electricity gets induced. This whole principle, it's Faraday's law of electromagnetic induction. Michael Faraday figured this out way back in 1831.
Amazing. So that's the bedrock.
It's the fundamental science, and it's why AC, with its inherent change, is perfect for transformers. It's this beautiful, synchronized dance between changing electricity and changing magnetism.
A dance. I like that.
Okay.
Okay, so electricity makes a changing field. The iron core delivers it. The changing field makes electricity again. But wait, the whole point was to change the voltage. How does that part happen?
Ah, yes. The transformation itself.
We have the primary coil getting the power, the secondary coil giving it out. How do we actually make the voltage go up or down? This involves the turns, right?
Exactly. The number of times the wire is wound around the core on each side, we call it the turns ratio. And this is where the design is just beautifully simple and effective. The output voltage on that secondary side, it's directly proportional to the number of turns on its coil compared to the primary coil.
Directly proportional. So
Yeah.
like double the turns, double the voltage.
Precisely. Let's use an example. Say the primary coil, the input side, has 100 turns of wire. And let's say we feed it 200 volts AC.
Okay, 100 turns, 200 volts in.
Now, if we want to lower the voltage, step it down, like we do for homes, we wind the secondary coil fewer times. Let's say we wind it only 50 times.
Half the number of turns.
Exactly half. So the output voltage will
It's
be
100 volts.
exactly 100 volts out. It's a simple, reliable ratio. Fewer turns on the output side gives you lower voltage.
That's surprisingly straightforward. Less winding, less voltage.
Isn't it? And the opposite is just as true. If you want to raise the voltage, step it up, like they do for sending power long distances.
You wind the secondary coil more times.
You got it. Same setup. 100 turns, 200 volts on the primary. Now let's wind the secondary coil 200 times.
Double the primary turns.
Right, so the output voltage will double as well. You'll get 400 volts out.
Wow. Just by changing how many times you wrap the wire.
Just by changing the turns ratio. This ability to precisely control voltage up or down just by adjusting windings, that's the practical magic of Faraday's law. No complex electronics needed for the basic function, just physics.
And this ties back to the efficiency thing.
Absolutely. Remember, power is voltage times current, PVI. Transformers are very efficient, so power in roughly equals power out, ignoring small losses.
Okay.
So if you step up the voltage, say double it.
The current must go down by half to keep the power the same.
Exactly, and that's the key to long-distance transmission. You crank the voltage way up, the current drops way down, and those I²R heat losses become tiny.
It all connects. High voltage, low current, low loss.
That's the strategy. Then closer to homes, you use step-down transformers to bring the voltage back to safe, usable levels, which brings the current back up for our appliances.
So we use different types. Step up at the plant, step down near us.
Yes. And there are others too, like isolation transformers for safety or auto transformers that use a single winding. Some even have multiple taps on the secondary coil.
Taps.
Yeah, connection points at different numbers of turns on the secondary winding. This lets you get several different output voltages from the same transformer. Very versatile.
That is clever. just tapping into the coil at different points.
That's flexibility.
Okay, so it's winding copper wire around iron.
Mhm.
And the number of loops dictates the voltage. You know, you'd think making something that powerful would need, I don't know, rare materials or super complex tech.
That's the common assumption, isn't it?
Yeah, but it sounds like maybe not. What's actually inside these things?
Well, this is where it gets really interesting because fundamentally, you're right. It's surprisingly basic materials.
Like what?
Primarily, it's copper wire for those coils and iron for the core.
Just copper and iron. Seriously.
For the main active parts, yeah. Copper is a great conductor for the coils, and iron is excellent for carrying that magnetic flux in the core. It's not about exotic stuff. It's about arranging these common materials in a really smart way.
Okay, tell me more about the arrangement. It can't just be loose wire on a chunk of iron.
Definitely not. The copper wire used is special. It's called magnet wire. It has a very thin coating of insulation, like enamel.
Ah, insulation.
And that's absolutely critical. It looks like the wire is bare and round right on the core, but each turn is electrically isolated from the next turn and from the core itself.
Why is that so important?
Because if the turns touched electrically, you'd just have a short circuit, a big lump of copper. The current wouldn't flow in nice loops to create the magnetic field properly.
Right, it would just take the shortest path.
Exactly. So the insulation ensures the coils are magnetically linked through the core, but electrically separate. That's vital for the induction process.
Okay, magnetic connection, electrical isolation.
Yeah.
Got it. And the iron core. Is it just a solid block?
Usually not, especially in AC transformers. To make it more efficient, the core is typically laminated.
Laminated, like a poster.
Sort of. It means the core is made of many thin sheets of iron stacked together, but each sheet is insulated from the next one, maybe with a thin layer of varnish or oxide.
Why do that? Why thin sheets instead of one solid piece?
It's to combat something called eddy currents. Remember that changing magnetic field?
Yeah.
Well, that changing field doesn't just induce current in the secondary coil. It can also try to induce small swirling currents within the iron core itself.
Okay, and that's bad.
It is, because those eddy currents just generate heat in the core. It's wasted energy.
Yeah.
By using thin insulated laminations, you break up the paths for those currents, making them much smaller and reducing the energy loss. It's a clever trick to boost efficiency.
Huh. Thin sheets to stop unwanted currents.
Smart. So that explains why transformers can be so heavy, right? All that copper and iron.
Definitely, they are dense, but the structure itself is fundamentally simple. Coils, core, insulation.
And you mentioned larger ones need cooling. Oh yes. Smaller ones might just be air-cooled, but the big ones you see in substations generate significant heat. They're often filled with a special mineral oil.
Oil. Inside a transformer.
Yep. It serves two purposes. It's a great electrical insulator for the high voltages inside, and it circulates to carry heat away from the coils and core to the outside, often through cooling fins or radiators you see on the tank.
So the oil cools and insulates.
Exactly. It keeps things from overheating and failing. The whole assembly coils, core, oil, is typically housed in a strong steel tank with insulated connectors called bushings for the external wires.
It sounds incredibly robust.
They have to be. And because there are no moving parts, really, they can last for decades with relatively little maintenance. That reliability is crucial for the power grid.
So, simple materials, clever arrangement, robust design. No wonder people are surprised when they take one apart.
Right. As the source material mentions, people expect complexity, but they mainly find copper and iron, just arranged very precisely.
And the type we've mostly described, with two separate coils, is called?
A two-winding transformer. That's the most common type. And the voltage change, as we said, boils down to that elegant turns ratio.
Amazing. Okay, let's loop back to the current war. Edison's DC versus Tesla's AC. You said the transformer was AC's knockout punch.
Absolutely. It was the decisive factor.
So why couldn't DC use this fantastic simple device?
Yeah.
If it's just copper and iron, why the limitation?
It goes right back to that core principle, the changing magnetic field.
Okay.
Think about DC, direct current. What's its nature?
It's constant, right?
Yeah.
Flows in one direction, steady voltage, like a river, you said.
Exactly. Constant voltage, constant direction. So the magnetic field it creates when flowing through the primary coil is also
Constant. Static.
static. It doesn't change. It doesn't pulse or reverse. And if the magnetic field isn't changing,
And Faraday's law doesn't apply. No change, no induction in the secondary coil.
you've nailed it. Put DC into a standard transformer and the secondary coil just sits there. Silence. Nothing happens. The dance requires change and DC doesn't provide it.
Wow. So DC is fundamentally incompatible with this type of transformation,
Correct. Now contrast that with AC.
which is all about change.
Constantly changing. Its voltage rises, falls, reverses direction 50 or 60 times every second. It's inherently dynamic,
So the magnetic field it creates is also constantly changing.
continuously changing, pulsing, reversing. And that dynamic changing field is perfect for inducing a current in the secondary coil, according to Faraday's law. The secondary coil feels that constant magnetic fluctuation and responds by generating its own AC current.
So AC and transformers are like a perfect match.
A perfect synergy. And the impact of that synergy was world-changing. First, long-distance power transmission.
Because you could step up the voltage super high.
Hundreds of thousands of volts, yes. Which means very low current for the same power, drastically cutting energy loss over hundreds of miles. Then you step it back down near the users. This ability basically built the modern grid.
Allowing power plants to be far away.
Exactly. Which leads to the second big impact, flexible power plant location. No longer did plants have to be right next to cities.
You could build them near fuel sources or rivers for hydro, or just out in remote areas.
Right. Near resources, or where environmental impact could be managed better. A huge leap for industry, for cities, for everything.
It really underpins so much. But it's important to remember what they don't do, right?
Absolutely crucial. Transformers are voltage and current changers. That's their job. They cannot change the frequency. 60 hertz in, 60 hertz out.
And they don't make power.
No, they don't create energy. They just convert it between voltage levels. Power in equals power out, minus those small efficiency losses we talked about, like heat from resistance and eddy currents. They obey the laws of physics, conservation of energy.
So no free lunch, just repackaging the energy.
A very efficient repackaging, but yes. Now, it's worth a quick mention. Modern tech can transmit DC over long distances now, using HVDC, high voltage direct current.
Ooh. But I thought DC didn't work with transformers.
It doesn't, not directly. HVDC systems use complex electronic converters, big semiconductor stations to change AC to high voltage DC for transmission, and then back to AC at the other end.
So electronics instead of simple transformers.
Right. It's used for very specific cases, like extremely long distances, underwater cables, or connecting grids that aren't synchronized. But for the vast majority of the grid we interact with daily, the AC transformer is still the workhorse.
Okay, that makes sense. HVDC is a special case, but AC and transformers are the norm.
Overwhelmingly so.
So wrapping this up, it's kind of amazing. Just copper wire, carefully wound, laminated iron, cleverly shaped,
Yeah.
all working together using changing magnetic fields.
Simple components, profound result.
And that gives us the backbone of our entire electrical system, that aha moment of the magnetic connection, the turns ratio. It's pure physics applied beautifully.
It really is a device everywhere, silently powering our lives, often completely unnoticed.
Just humming away.
Indeed. And, this raises an important question as we look ahead. Well, considering how vital these transformers are, how utterly fundamental to modern life, what happens next? Our energy demands keep growing, right? We're adding more renewables like solar and wind, which can be intermittent. Smart grids are becoming a thing.
Things are getting more complex.
Definitely more complex, more dynamic, more distributed. So how might these devices, these transformers built on 19th century principles, need to evolve?
Can simple copper and iron keep up?
That's the question. Will they need to become smarter, more efficient, maybe integrate new materials or control systems we haven't even thought of yet? How do we ensure this simple, elegant workhorse can handle the energy challenges of the future?
That's a really good point. It makes you think about all the hidden engineering just keeping the lights on.
It certainly does. Makes you appreciate that quiet hum a little bit more, doesn't it?